Hello everyone. Miodrag Milanovic is going to give us a lecture about making a new toolchain for GateMate FPGA. Thank you very much and give an applause.
Thank you. Okay, well, let's start. Let's first do a little introduction. So I'm an open source EDA developer in IOSIS HQ, and I'm working in software developer since 2000. And yeah, reverse engineering is my greatest passion. So I always try to be in open source and do some reverse engineering while doing it. And some of you may know me from some completely different unrelated project to this, like MAME or some other smaller open source project. I'm also author and maintainer of OSS CAD Suite, and that is a way of packaging various open source EDA tools in one package that is useful, and easier than to install on various, on your own machine or on a CI. And yeah, I was also involved in the development of NextPNR from early beginning, so yeah, one of the authors or original authors of it. So yeah, we did now mention a lot of buzzwords here, and maybe not all of you are familiar with terminology here. So yeah, let's do some small look into what we are going to talk about. So we mentioned FPGAs. So these are field programmable gate arrays. So you may, you heard about integrated circuits, of course, and there are of course some large-scale application-specific integrated circuits like ASICs that are created to work some specific job, like you have some CPUs, you have some MCUs, you have additional DSPs or whatever. And of course, that is the process of developing them is quite long, and it's quite expensive to build your own ASIC. But there is a cheaper solution, so you can use FPGAs and create your own hardware in a short amount of time. And to do that, you would use some of the HDLs, so hardware description languages, to describe that hardware. So you are actually not programming, but you are creating hardware by writing in a syntax of Verilog or VHDL. And for complete, let's say, a set of tools that we use for design automation, we call electronic design automation, and those are EDA tools. So here also on the picture you can see one of the boards that is used for development, and that is exactly the board from Cologne Chip, which is using the FPGA we are going to talk about. We need first to know how the complete design flow looks like for an FPGA. And that's a bit different than when you're creating software. So here you have a input that is usually in Verilog or VHDL, and for simplicity, and we are going to use, just to mention here, the open source tools and tools that are specific for this project. So we have a first step is the synthesis that converts the initial Verilog netlist to a netlist in an internal, let's say, format that is basically mapped to primitives that exist on the real hardware. And for that one, we are going to use IOSIS, which is a open source synthesis tool, to convert the netlist to and to create a representation in the real hardware, we need to do a place and route. And place and route is a process of actually placing all those primitives all around the FPGA and connecting them and basically creating a routes between each endpoint. And for that, we are going to use NextPNR. NextPNR produce text-based format bitstream just because it's to basically prevent, to make easier debugging and to make it agnostic to actual final bitstream. So you can do additional altering of the bitstream afterwards because it's human readable. And then we actually need to package that text bitstream into binary bitstream. We have a tool for that. And of course, we need to program the FPGA, and we are going to use the Open FPGA loader, which is also open source. So in total, we have here 4 different open source tools, and we have complete flow done with the open source tools. Here we are going to talk about the GateMate FPGA. So this one is a bit specific because it's European FPGA. It's made by Cologne chip, and yeah, as you may see, it's a 29 nanometers Global Foundries fab that's producing. It's produced in Global Foundries fab, but it's 29 nanometers process. There are, you have a here specification. It's let's say nothing jumps out there in the specification. It looks like any other FPGA. But if you take a look at the image on the side, and you may notice, for example, here we are mentioning A1, A2, A4. Those are the multi-die chips. So what they did, and they patented, is they produce one type of die on the hardware, and then when they are cutting the wafer, they can basically cut parts of 4 that are connected, and you get a A4. If 2 are connected, you are getting A2. Not all combinations there are possible, but because they already have a predefined die-to-die connections, and you are actually just putting, you can create from one wafer basically multiple types of FPGA. And so far, they have released A1, A2, and A4, but there is possibility of basically building that up. So what is specific for this architecture is also that they are using so-called CPEs, so-called Clone Programmable Elements. And yeah, as you may see, those are not LUT4s. So you can basically generate any logic function that contains 4 input and 1 output with a LUT4. And what they did is they use LUT3. So they have multiple LUT2s that they are just connected into 3. And that actually requires half of the bits to configure. So basically with the, for one CPE that contains 8 inputs and 2 outputs, you are actually spending same number of bits that you would use for the LUT4, one LUT4. And that is, that's saving space, let's say, making it cheaper. And of course, in one CPE, you can also, you have a logic that you can use for adders, and you can also use it to have a 2x2 multiplier. Of course, the other thing here is that complete mesh of is connected over using the switch boxes. And there are 2 types, big and small switch box. And you can see here that there is something which is very specific for the FPGA, this FPGA, that there are also diagonal connections. That's quite unusual for the FPGA. Usually you have just a horizontal or vertical connections, and the small ones means that you can connect just to the next big switch box, and one small on one side and on the other. But for the big ones, you can also do basically 2, 4, 8, I think 12, 16, and 20. So basically, you have a much more possibility of connecting things, and to do basically the to allow signal to travel fast, on a greater distance, we have also these SB drives that are just amplifying the signal, making it possible to reach the other part. And as you may see here on the image, all the inputs for the CP block must come through the input mux, and they are feeding the output mux, but they can also feed the switch box. And like here, it's connected to the IOs. The IOs are, and every basically other non-CPE part is connected through the CPE, and you need to use the CPE to drive it. So how do we create support for new architecture? And first thing we need to do, of course, is always to familiarize with architecture. We would need to create a synthesis support for it. We need to create a place and route support, which includes bitstream manipulation tools. We need chip database and all the data, how everything is connected. So we need to know the routing graph and all the primitives. And yeah, based on that, we can then build the next PNR and basically be able to use it. So the good big thing is that Cologne Chip is actually using and supporting open source and endorsing it. So from the beginning of this project, we did everything in the public. The project that we built for this is called Project Peppercorn, and basically it's funded by BMBF, so Federal Ministry of Research, Technology and Space in Germany. And yeah, it's a pun name basically because the names are, A1, A2, and that is exactly the name how the peppercorn trains were called in UK. so that's the.
Is there also a commercial toolchain for this? Or is
there is currently a commercial tool which is freely available, but it's quite. It's a tool that was developed for a long time, and basically it's hard to maintain and it's hard to add new features. And then, it's used for various other things as well during the design process. So it complicated basic development for them. And here you can see also the links for all the projects that are basically contained under this. As for the familiarization with architecture, well, you need to read the manuals in short. It's hard to do it other way, and we did got the complete documentation. Of course, not everything is in documentation. We also did got the vendor tools, even the source code for it. But yeah, it's you just need everything to double check everything when you are familiarizing with something, and you need to create your own test examples, try out, see how it's what their tool is currently working, and so on. What we need to take to mention here is that their tool is only supporting A1, so one die FPGA version, but not multi-die. So that's something that's completely unique to for the next PNR support. Yeah, for the user support, we have luck because the Cologne chip actually already did have the support for in IOSIS. And how do we actually start with this is that we start by adding just a support for LUTs and flip-flops. And then you can basically create any project that just by using LUTs and flip-flops, it will not be performant, maybe it will not meet the frequency required, but for a small examples is good enough just to test and to be sure that that you understand at least that on that level. And what that usually also means is that you need to write your own simulation models so you can try test out later and to have the equivalence check to actually confirm that. And then yeah, like a drawing on all, so you make it 2 cycles and then yeah, you just draw the rest. And yeah, that's how it's basically done for the IOSIS. So it's a gradual process of making it part by part. For the bitstream manipulation tools, it's a reverse engineering task. So you usually just look at the number of bits and trying to see how they are forming the messages. Usually they are programming over JTAG, and then you can see some patterns and repeating and so on. And of course for this we got the documentation. So yeah, there was not much of the reverse engineering task, but for the other things we did in past, it was purely reverse engineering. Here we needed to confirm, of course, some of our findings, because not everything is always clear, of course. And yeah, because we usually start with this kind of tool, because you would first what would you do first is to take existing bitstream created by their tool and then try to unpack it. So basically create a textual representation of that to understand how things are connected. And yeah, so you have an example here how the textual representation would look like. So you have a tile position, and you have then the primitives and basically their configuration and how that basically explains how things are connected. So this is something that would be generated by the XPNR, but also we can take existing bitstream and convert it to this kind of format, and then yeah, you can basically use that to reverse engineering existing bitstream on an FPGA. So yeah, to create a chip database, of course we need to know all the hardware primitives, but also we need all the routing information. And usually you have some external files that already have that in them, but in this case everything was code generated. So there was no data files. And so even if we have the access to the source code, it was actually quite useless to have it. I mean, you can read some of the things, but still there is no way to confirm. And what we did is then we basically create a Python code that will be used as a code generator that will create all those connections between the specific parts and basically based on the documentation, and then we would check that against their code or against some of the by just trial and fail, basically. So to build an XPNR support, basically you need to understand that there is a PNR workflow consists of loading a netlist, packing those primitives, placing them, routing, and then, of course, at the end, generating a bitstream. So we do have some generic algorithms in XPNR, and there is Himbachel API that is just additional layer on top of it that enables you to just easier access to some of the most common architecture APIs. And what we start with is a packing procedure, and that packing procedure actually is used to map some of the HDL primitives to a hardware primitive. And as I mentioned, you have a CPE that is basically consists of the lat trees, but in your design, you would have, you would just have some expressions. Those expressions will be converted by IOSIS to a set of such primitives, and then we can package, for example, 2 of those lat trees into one CPE. So basically, you are trying to make space taken by the design small as possible. So that's one idea, but also you're trying also to place it in such a way so you can reach a higher performance. So if something is possible only to connect by placing it nearby, on the next CPE, you are going to place it in such a way so the routing is possible and the routing is fast. And of course, there are some things that you can pre-place, and you need to pre-place, and those are IOs, PLLs, and global buffers, because depending on the board you're developing, pins are, just on that place, and you cannot move that, and you cannot put it on an arbitrary location. So you have a constraint file which is telling you, okay, you need to put this signal on this IO. And this is what you're doing in pre-placement, and then based on that, the placer will try to place the rest of the logic nearby. You may see here the placement, how it looks for one of the CPUs, but you can see here on the right side IOs. That are taken. There are small dots on the right side, but at the middle you can see 4 rows. Those are basically block ramps, and there is a nearby logic because there are just too many constraints here, because only certain CPs can feed that block ramp. So you need to put it on a certain place, otherwise it will just not work. And of course, you're doing the placing, we are running placing algorithms, which is same as for any other architecture. So and then we are doing some post placement and post routing, in which we are actually using some features like bridge mode, which enables us to use the CPs to propagate a signal, or while exporting, for example, bitstream, we need also to fix some inversion of the bits. So you see that this process is really step by step, and there are too many things that could go wrong. And yeah, everything is just validate. You need always to compare pre-place and route and post-place and route netlists. So what we did is NextPNR can export a routed netlist in a JSON format, and that JSON format can be loaded back into IOSIS, and IOSIS can produce Verilog based on that even. So what we are using is Equi tool that is used for equivalence checking, and we are basically then running equivalence between the input and output, and that works for smaller designs, but you can then be sure that you at least have packed things correctly, and that if you are changing some logic or optimizing, that you didn't affect the bitstream and the logic at all. And you again need to try that on the hardware, because it can sometimes not work on the hardware, because there are various things that we also did. So we did as well packing, we did the bitstream conversion. We didn't know if the chip database is actually right. So we need to validate part by part each part of that and try that again on the real hardware. So we made a large base of the designs, trivial and small and really large, and big kudos to Litex. They do have a really nice Python-based tool that enables you to create various designs using RISC-V CPUs. So you can even create a big two-core CPU that is capable of booting Linux, and So this is something that we performed during the complete work. And we need to know that not all FPGAs are made same. We saw that there is a LUT2 trees instead of LUT4 and LUT6 that are quite usual in other architectures. But here, to reduce the cost, designers were using inverters on some places instead of buffers, because it's essentially doing the same thing. I mean, it's amplifying the signal, but it also inverts the signal. And then that was actually quite annoying, because a lot of time we spent on validating which parts are actually inverting and which are not. So some routes were and some were not. And actually it was also depending on position, because depending how long you are jumping into other tile, you may or may not go through a number of inverters. Meanwhile, so that is something that's quite different than other FPGA, but also due to the same reason, there is no predefined clock tree, and because there is no predefined clock tree, that means that you need to create your own clock tree, and creating a good clock tree is actually not a simple job. So idea is that when you have a lot of CPEs, each of them also contains 2 flip-flops, and ideally you would like to, for global clocks that are used, that all the clocks come to all flip-flops in the same time. I mean, that's not possible, of course, but near the same time is good. But here you are using regular routing network to actually route that signal. So what we needed to actually do was to try to find the shortest route and to first route the clocks. First what we are doing is we are trying to route all the clocks through the sources and to make that minimal as possible. And also it would be good to try to make that that the numbers are nearby. So sometimes if otherwise you will get the clock skew problems on it. And of course, there is a thing that there for the synthesis does not map to the multiplier cell, so we are not mapping to the CPE, but it's mapping to one cell that actually represents a multiplier. And of course, the multiple dies do not share the clock signals, so they do have die-to-die connections, but things that are connected, clocks are not one of them, so you need to individually configure the clocks, and that makes placement then a bit different. And here we have a clock routing, so how it's done, how it's basically distributed in this FPGA. And the limitation is also that you have only 4 signals. And as I said, the only way was actually these in the middle are just to distribute the clocks to the block RAMs, but not to the other parts of logic. And you basically need to go and find the shortest path to the one of the edges. Otherwise, you have a clock skew problem. And for the multipliers, well, we have one cell, but good thing is that actually we developed the separate placer, and that placer will manually generate all the cells that are needed to actually implement that multiplier, but it will also constrain them to be on exactly needed locations, but also will route the signal through desired paths, because of course there are some that are inverted and some are not. So and in this case you need to use inverted for connecting to the next level, otherwise you will have completely wrong logic. So yeah, and the main question is always, can you boot Linux? And we did manage to boot Linux, and it is done on the this board for now, because it was the first one that actually contained 64 megabytes of SD-RAM, and yeah, that was requirement is 32 megabytes of SD-RAM at least, and the official evaluation board have a HyperRAM. And yeah, we managed to get the HyperRAM working on this one, but that this one is 8 megabytes only, so it was not enough. But yeah, we are trying to. There are ways of squeezing the Linux to actually fit in the 8 megabytes footprint, so we can then we could boot that. And yeah, the cheapest solution for development was the first one we used. That's the Linux board. It's 50 euros, and basically it's the cheapest way to actually do the development for this one. And yeah, but it's only having this VGA and PS2, so that was not enough. Goran will talk more about that. And yeah, before I thank you all, I would just like to dedicate this talk to my mom that passed out this year, and I would like to thank everyone for support and that helped us on this project, especially Goran and the other colleagues that were working on this one. Thank you, everyone.
You had a lot of pieces in here to test that your bit stream was correct. Yeah. So you generate it, then you feed it back into Verilog, you test for equivalence, and I assume you could also emulate for equivalence, even though that would provide less coverage. So, and you have this model describing what the chip looks like that you create from its documentation.
Yes.
And if I were making that model, I would screw some part of it up. And it would be an absolute pain for me to debug where and why. Do you have any crazy debugging tricks or tools for catching those sorts of mistakes?
Yeah, I mean, regarding the layout on actual hardware, that's basically not that possible to check. What we did was, if it reaches the point where it boots Linux, then probably we did the logic right until then, because every during the boot process you have a lot of things that were actually executed. But on side of that, to actually do the equivalence checking, you have a original netlist, and that is just a pure Verilog. So there is nothing there. You can compare that to the synthesized Verilog. Then you have primitives, HDL primitives, that are nearly mapping to the hardware, but you have a simulation models for them, and you can compare that. But then on a third level, we have things that are how they're really in hardware, and then we needed to create a simulation model for them based on the schematics. When we compare the first to the last one, then we would see, if it really matches, because that will also involve some of the logic that basically you cannot directly understand maybe by looking just at the schematics, but this was, as you said, there are a lot of places where you can create a mistake. And that's why this process is just going back and forth, confirming part by part, doing the simple things like connecting this one button to a LED, and then trying to, route, or then what I also did is I was checking each of these IOs, and then trying, because those routes must take, everyone will take the different route, and basically I can see if IOs are configured correctly, if they are mapped correctly, and of course inverting part. I mean, first thing that happened is, okay, now it's powered on, I can press a button, it's powered off, and then okay, but next time it's depending on the route, it was reversed, and then we noticed that, yeah, there are some things that are inverting, but they're not there. And as logic grows, basically it becomes complicated. I may agree on that, yeah. Thanks.
So just when you're adding support for a new FPGA to the whole YOSIS next PNR, yep. I don't know, because those tools already support like many other FPGAs. Yep. What's the process? Is for example, YOSIS, is it just some engine which you write a description of the FPGA, or do you actually write the code to embed it?
This involves writing a code. So that's why we are separating things. So you have a project peppercorn repository which contains, just the tool for bitmap manipulation and basically ways to create a chip database. But on the next PNR side, each architecture have a specific code. But with the Himbachel API, we basically minimize that code by unifying the way how we store data in the chip database. So deduplication, compression of that, and routines for access, each part are basically same, and they do depend on data and not on the code. But for example, for packing and pre-placement, you need to do that basically coding manually for this architecture. And some of them will not require some parts, packing is always mandatory, but for example, post-routing or post-placing is, optional. It depends on the architecture. Here we had a lot of differences, like multipliers, like the clock tree, inverters, so we needed to handle that, because that's not something that's that often. So now we have a code that we may maybe in future share with other architectures. They try to use the same thing, so we can optimize more. Thanks.
Does it have any this FPGA? Does it have any protection against like getting bitstream out of it?
Yeah, this one doesn't. I mean, and this one can be programmed in several ways, but basically you have external flash that you can read, and I did work with some other FPGA vendors that they did have some redundancy even, or something like depending on for example for the Nano Explorer we did work, and I mean their board is quite expensive, but it's just radiation hardened, and also it's made to be run in space. So yeah, there are 4 different flashes that are used basically to program the same bitstream, and you have redundancy in everything. And but here there is no basically protection on that, and that was not the idea behind anyway, to have that protection. But usually they do have some encryption or a way to differently store the bitstream.
If I have the bitstream image as a binary file that I read out of the flash memory, does this toolchain provide me with what I would need to understand that bitstream and to maybe emulate it? I know it would still be painful, but
Yeah,
does it,
it's,
does it have the basic building blocks of that?
It's a partial thing. In this case, we didn't develop the complete reverse to a netlist, original netlist, or something like that. But you can get a human readable form of a bit stream. But the problem is that 0 in bitstream doesn't mean always that there is no connection, but that the default connection is used to connect 2 points. So you are sometimes not, it's not implicit if things are not connected, or you are using default connections. So you would need to go from basically all the configured primitives and then go backwards, forming if this is connected to something, or what would that be? If that exists, then it's connected. If not, probably there is no connection. So it's much harder, especially on this one, because that's the way how 0 doesn't mean not connected, but just default value, whatever that is, and that differs between the configuration parts. So yeah.
But that's automatic part which can be automated.
Yeah, that can be. It just that. Just please remember that this project was 1 year long, and we basically managed to get in the first few after 2 months. We basically get something to work, and then it was just adding part by part, validating, going back and forth. But it's the greatest pain is just to reach the first point when you have something. You have pressed the button and then lights goes on. I mean, it looks stupid, but here you're developing basically everything. I mean, in this case, we have a luck that actually Yosys existed support for it, but we found even bugs there, and they were actually preventing us of working designs for LiteX, for example. So block memories were not right.
We have time for one more question. Okay, thank you, Miodrag, very much for the great lecture.